Hello, my name is Skylaris. I am leading the work package on the cross-cutting activity of development of methods for simulations of the essential physics and material science of batteries. So my talk is going to give you an outline of the developments we have been doing. So basically building a platform for large-scale quantum atomistic electrochemistry simulations of batteries. And more detailed talks with more examples are going to be given by Jacek Diedic and Arihan Bandari, who will follow after my talk. So my background is in quantum chemistry methods, quantum mechanical calculations of materials. These methods are very widely used because they are very powerful. The same approach can be used to give us all the observable properties. We can compute all the observable properties of atoms and also molecules and materials. So for example, here we can compute their excited states and spectra, but we can compute essentially all observable properties. It's a very powerful approach, the quantum mechanical description of materials, and there are two methods, two main approaches that we can use for these calculations. One is the original wave function theory formulation of quantum mechanics, which is, however, very costly. It is limited only to a few tens of atoms. And then the more modern approach of density functional theory, which is a reformulation that uses the density, the electronic density as the central quantity and can scale to larger numbers of atoms. So what do we do in density functional theory in DFT simulations? We need to calculate the energy of a material, and once we have done this, we can use such calculations to do dynamics, to obtain dynamical properties. We can obtain structural information, chemical reactions, and so on, and also excited state properties such as spectra and so on. So the central goal is to calculate the energy of a molecule, and this is not an easy task. As we will see here, when we do a density functional theory calculation, we need to follow an iterative procedure for the calculation, starting from a guess for the electronic density and then refining it as we go along. And every step in this process is very computationally demanding. We need matrix operations, difficult integrals to calculate, and so on. So it is no surprise that the computational effort of DFT calculations is large, and most annoyingly, it has a bad scaling. So it scales with the third power in the number of atoms. As you can see here, as we increase the number of atoms in these calculations on segments of graphite, the computational effort hits a bottleneck after a few hundred atoms. So it is limiting in the terms of things we can study. Now, in my research, I have been working on the development of methods for large-scale DFT calculations for overcoming this cubic scaling barrier. And the method we have been developing is called ONETEP. It's the ONETEP program, which achieves linear scaling computational effort. So the computational effort increases linearly with the number of atoms, but most importantly, we do this while retaining the same level of accuracy as conventional density functional theory. So there has been a lot of developments that I cannot possibly fit in one slide. But the main message that I want to pass to you is that we have the same accuracy as cubic scaling DFT, and we achieve this by having two levels of resolution and localization. So basically, in this iterative procedure is split into two levels, and we have a coarse level of resolution here and a final level of resolution here in this loop. So as a result, we can see the scaling that we have with this method. We can do calculations on tens of thousands of atoms. This is the same plot with the conventional DFT, and these are calculations with ONETEP. where you can see we can push these graphite segment calculations to tens of thousands of atoms. And this is not just graphite, it can be any material, any configuration. It can be applied fully generally to any combinations of atoms. So we can build much more complex models, for example, for interfaces such as in battery electrodes. So our work here has been focusing on taking these accurate calculations and embedding them into electrolytes, so developing a hybrid atomistic continuum solvent and electrolyte model. So it will allow the calculations to happen in the environment of a battery material. We have a rigorous linking of the electrostatics and other interactions between the atomistic description of the electrode and the continuum description of the electrolyte, as you can see here. So we have a multi-scale, multi-resolution approach, which is computationally tractable and allows us to describe the physical effects, such as the double layer formation and the effect on the energy and electrostatics of intercalation, for example. So to do this, we needed to do a further step in our calculation. We needed to develop an electrolyte model that solves essentially this so-called Poisson-Boltzmann equation with an efficient multi-grid solver that we developed with our collaborators. And in the end, in the usual two-loop procedure of ONETEP, we also have this procedure for solving the electrostatics with the surrounding electrolyte medium. So this is an example of how it works in practice. These are calculations on graphite with lithium intercalated, and you can see, this is a very simple model just to give you an idea of what you could do in actual calculations. So this is the lithium inside graphite, and you can see the electrolyte profile, concentration profile here. You can see the negative electrolyte around the positively charged lithium ions, and then negative electrolyte, positive electrolyte further away. And this is the concentration profile when the lithium is outside. And we can also obtain here the electrostatics. So this is the electrostatic potential of the whole system, electrolyte and electrode. You can see how it changes here with the presence of lithium, whether it is inside or outside the electrode. So to conclude, we have been developing new software tools for multi-scale electrochemical simulations, and our aim is to capture the essential physics of batteries and also to provide parameters for bridging atomistic to larger scales. So this can be used to also bridge to scales such as Newman models, which are used for larger scale simulations. Also, the models that we are controlling are, the models that we are developing are controlled by experimentally relevant parameters, such as the applied voltage. So we can do constant voltage, constant potential simulations, as Arihant Bhandari will show in his talk. The next step in our developments is to include also some kind of atomistic description of the electrolyte as well, so we can simulate chemistry at interfaces, such as the degradation reactions and SEI formation that happens at interfaces, which is perhaps one of the most important areas that one needs to understand. And the ultimate goal is to develop a platform for ab initio electrochemistry simulations within the unique linear scaling framework of the ONETEP code that allows us to have models with realistic complexity. I would like to finish by thanking the people in my group that have been working in this area, and our collaborators in Southampton and our collaborators outside Southampton in Biovia, Biovia is the company via which we make our developments available into the commercial version of the ONETEP code. also Lucian Anton, who is the main developer of the multigrade method. So thank you very much for your attention, and I hope I will see many of you in the Q&A session on the 28th of April.